Hello, viewers. You're welcome to this lecture series on soil science and ecology. In today's lecture, we're going to look at the chemical properties of soil, the chemical properties of soil. Now, there are 5 chemical properties of soil we want to discuss today, and those chemical properties of soil include cation exchange capacity, anion exchange capacity, soil reaction, which is pH, base saturation percentage, and soil buffering capacity. These are the 5 chemical properties of soil we're going to discuss today. Now, first, we want to look at cation exchange capacity. What is cation exchange capacity? Cation exchange capacity can be defined as a measurement of the magnitude of the negative charge per unit weight of soil. It is a measurement of the magnitude of the negative charge per unit weight of soil. Cations are positively charged ions. And for a soil to retain these cations, it must have negative charges to interact, to react with the positively charged ions or positively charged plant nutrients, which are cations. So the measurement of the negative charges that a soil has is actually its cation exchange capacity. And usually clay soils tend to have negative surface charges, and these surface charges enable them to retain soil nutrients. Okay, so it is defined, or it can be defined as the measurement of the magnitude of the negative charge per unit weight of soil. Cation exchange capacity is also defined as the amount of cations a particular sample of soil can hold in an exchangeable form. Okay, the amount of cations a particular sample of soil can hold in an exchangeable form. Okay, both definitions have one thing in common: the ability of a soil to retain cations. Okay, to retrieve cations from the soil water solution and make them available to plants for absorption, because most soil cations are actually plant nutrients. Okay, so the ability of the soil to sequester these cations and make them available for plants is what we call the cation exchange capacity. Okay, now cation exchange capacity can also be defined as the number of exchangeable cations by dry weight that a soil is capable of holding at a given pH value and available for exchange with the soil water solution. Okay, it can also be defined as the number of exchangeable cations, exchangeable cations at dry weight that a soil is capable of holding. Okay, the number of exchangeable cations. The soil, a soil that has cation exchange capacity is able to make the cations available to the plants. Okay, they sequester some and the soil water solution, and then retrieve them for plant use, and excess cations are still kept in the soil for future use. So the ability of the soil to make exchangeable cations available at a given pH value is basically what cation exchange capacity is. So it is defined as the number of exchangeable cations per dry weight that a soil is capable of holding at a given pH value and available for exchange with a soil water solution. Some plant nutrients and metals exist as positively charged ions or cations in the soil environment. Among the more common cations found in soils are hydrogen, aluminum, calcium, magnesium, and potassium. So these are positively charged ions or cations. Okay, hydrogen, aluminum, calcium, magnesium, and potassium. Most heavy metals also exist as cations in the soil environment. Most heavy metals also exist as cations in the soil environment. So cation exchange capacity is a very important property of soil because it is also able to retain some of these heavy metals, okay, and prevent them from leaching to the groundwater, okay. It's able to retain some of these heavy metals in the surface of the soil and prevent them from leaching to the groundwater, which would have serious health impacts on humans. Cation exchange capacity is used as a measure of soil fertility, nutrient retention capacity, and the capacity to protect groundwater from cation contamination. Okay, it is used to measure soil fertility. Soil fertility is enhanced by the cation exchange capacity of the soil because the nutrients that plants require to grow must have to be retained. And it is because of this property, this chemical property, cation exchange capacity, that these soil nutrients are made available. Okay, so soil fertility, nutrient retention capacity measured with cation exchange capacity. And the capacity to protect groundwater from cation contamination, that's cations such as heavy metals and other very toxic substances, is made possible. The protection of groundwater from these cations is made possible because of cation exchange capacity. Cation exchange is an important mechanism in soils for retaining and supplying plant nutrients and for absorbing contaminants such as heavy metals. It is expressed as milli equivalent of hydrogen per 100 grams of dry weight of dry soil. Okay, the cation exchange capacity is expressed as milli equivalent of hydrogen per 100 grams of dry soil. So, and the SI unit is centimole per kilograms. The SI unit is centimole per kilograms. The next chemical property we want to look at is anion exchange capacity. Anion exchange capacity. And what is anion exchange capacity? Anion exchange capacity is defined as the soil's ability to remove anions from the soil water solution and sequester those for later exchange as the plant roots release carbonate anions to the solution. Okay, the ability of the soil to remove anions from the soil water solution. Okay, the soil is able to remove anions from the soil water solution and sequester. Okay, sequester means to save or to put into isolation. Okay, for later exchange. So cation exchange capacity, anion exchange capacity is the opposite of cation exchange capacity. That's to say that for soil to have the ability to remove anions from the soil water solution, that soil must have positive charge. Okay, so there are some soils that tend to have positive charges, particularly those colloids which have low cation exchange capacity tend to have some anion exchange capacity. Okay, so the soil colloids that are low in cation exchange capacity tend to have anion exchange capacity. Amorphous and sesquosite clays have the highest anion exchange capacity, followed by the iron oxides. So amorphous and sesquosite clays, okay, clay soils tend to have the highest anion exchange capacity. Levels of anion exchange capacity are much lower than for cation exchange capacity. Phosphates tend to be held at anion exchange sites. So now these are some of the anions that exist as plant nutrients. We have phosphates, that's negatively charged ions. Okay, anions are negatively charged ions. Phosphates, sulfates, nitrates, chlorine. And these essential plant nutrients would have to be retained, and anion exchange capacity makes it possible. So sesquozide and amorphous clay are very good at retaining these plant nutrients and making them available for plants to absorb. Anion exchange capacity decreases with increasing pH. So when as the pH is increasing, anion exchange capacity decreases. Okay, so it's inversely proportional to the pH of the soil. So the increase in pH results in decrease in anion exchange capacity. Now I want to look at the next chemical property of soil, which is soil reaction or pH. And what is soil reaction or pH? Soil reactivity is expressed in terms of pH. By definition, pH is a measure of the active hydrogen ion concentration. It's a measure of the active hydrogen ion concentration. It is an indication of the acidity or alkalinity of a soil, and also known as soil reaction. Okay. The acidity or alkalinity of the soil is referred to as the pH, or it can also be defined as a measure of the active hydrogen ion concentration of the soil. More precisely, it is a measure of the hydrogen ion concentration in an aqueous solution. Okay, pH is a measure of the hydrogen ion concentration in an aqueous solution. So the pH scale actually ranges from 0 to 14. Okay, and the value 7 is known to be neutral. Okay, so values that are below 7 are acidic, while the values that are above 7 are alkaline. The values that are above 7 are alkaline. A pH value of 7 is considered neutral, where hydrogen and hydroxyl ions are equal, both at a concentration of 10 raised to power 7 moles per liter. Practically speaking, for soils, pH ranges from 3.5 to 9.5, as pH values beyond those extremes are toxic to life forms. Okay, for soils, the pH values range from 3.5 to 9.5. Okay, any value that's beyond this point is actually toxic to life forms. The most important effect of pH in the soil is on ion solubility, which in turn affects microbial and plant growth. So pH is very important in ion solubility. The solubility of ions, the ability of these ions to be properly mixed or dissolved in in water. Okay, the ability of these ions to properly mix with the water is made possible by the pH, or is determined by the pH of the soil. And it also affects microbial and plant growth. Okay, the pH of the soil determines the kind of microbes that can grow or that can survive in the soil. And it also determines the ability, it also determines whether plants will grow on a particular soil or not, or the specific types of plants that can survive. It also affects some soil-dwelling organisms, such as some benthic organisms. The distribution of these organisms is also determined by the pH of the soil. A pH range of 6.0 to 6.8 is ideal for most crops because it coincides with optimum solubility of most important plant nutrients. Okay, a pH value of 6.0 to 6.8 plant nutrients are more soluble. So this pH range 6.0 to 6.8 is ideal for most plants. In acidic soils, Hydrogen and aluminum are the dominant exchangeable cations. The latter is soluble under acid conditions, and its reactivity with water, that's hydrolysis, produces hydrogen ions. Calcium and magnesium are basic cations. As their amounts increase, the relative amount of acidic cations will decrease. So when calcium and magnesium cations increases, okay, the amount of the acidic nature of the soil decreases. Factors that affect soil pH include parent material, vegetation, and climate. So the parent material of the soil determines the pH of the soil or affects the pH of the soil. Vegetation, such as the conifers, when the soil under coniferous vegetation tend to be acidic. Then the climate also affects the pH of a soil. The climate also affects the pH of the soil. Some rocks and sediments produce soils that are more acidic than others. Quartz, rich and sandstone is acidic. Limestone is alkaline. Some types of vegetation, particularly conifers, produce organic acids, which can contribute to lower soil pH values. Okay, the conifers, okay, also tend to cause, like whistling pines and others, they tend to produce organic acids that affects the soil pH and make the soil to be acidic. They make the soil to be acidic. So I want to now look at base saturation percentage. Base saturation percentage is a fraction of the base forming cations that occupy positions on the soil colloids. Base saturation is almost in direct proportion to pH, and except for its use in calculating the amount of lime needed to neutralize an acid soil, it is of little use. Base saturation percentage is actually of little use. Now, soil buffering capacity. What is soil buffering capacity? The buffering capacity of a soil is defined as the resistance of soil to changes in pH and available cations from the addition of acid or basic material. So the ability of the soil to resist changes in pH and available cations is basically what soil buffering capacity is. So soil buffering capacity of a soil is defined as the resistance of soil to changes in pH and available cations from the addition of acid or basic material. So when acidic or basic materials are added, the ability of the soil to manage the pH, to resist changes in pH, is its buffering capacity. The buffering capacity of a soil increases as the cation exchange capacity increases. Okay, when cation exchange capacity increases, the soil's buffering capacity also increases. Hence, pure sand has almost no buffering ability, while soils high in colloids have high buffering capacity. So sandy soils tend to have no soil buffering capacity, but soils that are high in colloids, clay soils, tend to have high soil buffering capacity. Buffering occurs by cation exchange and neutralization. The buffering of the soil occurs by cation exchange and neutralization. The next chemical property. So we have looked at all the chemical properties of soil, and thanks a lot for watching. Please watch more of my videos from my YouTube channel, and you will be educated in soil science and ecology.